So the next periodic trend we're going to examine is atomic radius. All right? And the first thing we should note in atomic radius is what happens as things go down the periodic table. All right? So here I've got lithium, and after lithium I'm going to have sodium, and then potassium, okay, as I move down the periodic table. Now, lithium, as I go down the periodic table, I've got my 1s, 2 on the inside, and then on the outside I've got 2s1. Okay? When I go to sodium, similar thing, I've got 1s, 2 on the inside, then I go to 2s1, or 2s2, excuse me, and then on the outside 3s2. I come to potassium, 1s2, 2s2, 3s2, 4s2. So as I look at this radius, this encompassing radius, 4s1 there. As I look at this accompanying expanding radius, what I'm doing is adding more electrons to the outside. You want to think about this as kind of one of those everlasting gobstoppers, right? The bigger the gobstopper, the longer it's going to last, because you have to get down through more of the candy coating on the outside to get to that candy on the inside. Same thing here, all right? I've got to peel off the outsides like an onion. Now peel off these outsides to get to the center. The bigger the onion, the more skins I've got to peel off of that thing. All right? Essentially, because I move down the periodic table, I'm adding greater radius to it because my electron shells have to expand to accommodate more electrons. So moving down the periodic table, I see an expansion of the atomic radius. So, one way of looking at this is as I move down the periodic table, radius increases. All right? It's a little bit more nuanced when I move across the periodic tables this way. Right? And it would be better if I just showed you what the actual radius is. And let's see. This is in probably units. My guess is that. Let me just show you what these are. Aha! It's in picometers. I was right. Okay, so it's in picometers. And I'm going to write down what these values are. So lithium is 152 picometers. Okay. Now, without a comparison, we can't tell you if that's large or small for its table. So let's keep going down the periodic table. We'll look at the values for each one of these. And each one of these is in picometers. So then we go to 112. Okay. And then we go to 85, 77, and keep going to 75, 73, 72, and neon itself is 70. Okay. Now if we look at sodium and potassium, you'll be able to see that that's 186 and 227 to prove that I wasn't lying to you. Okay. The periodic trends of atomic radius, as we go this way on the periodic table, the atomic radius actually gets smaller. Why is that the case? You know, like with Dr. Owen, we just learned about shielding. Shouldn't the shielding be pushing electrons further away from that nucleus? Yes and no. Even though I've got a certain electron charge, this one, the effective nuclear charge is about 1.1, and well, this one's 5, it's still pulling those electrons closer to itself. And as a result, because it's pulling those electrons with a greater number of protons, I see an overall shrinking of that shell as I move from left to right on the periodic table. Okay? So, as I go this direction, with atomic radius, I see us going from larger to smaller. So from left to right, I go from larger to smaller. Okay? Now let's look at ionic radius, because it's directly related to this. So, abracadabra, I'll erase everything. Okay, so now if we think about ionic radius, what we're doing in this case is we'll be adding some electrons or removing some electrons from it. So if I look at lithium, right, lithium generally likes to lose an electron. If anything's a metal Metals in general like to lose electrons, okay? Because if lithium loses an electron, so here's its normal electronic configuration. If I lose an electron, I go down to the state 1s2. And that's helium core. Remember, that's noble gas configuration. Once I hit that, I'm going to be very stable. So lithium in general likes to lose, lose an electron in order to become more stable. Now, if you think about what that's going to do, I've got 3 protons, 2 electrons. So I've got a greater electronic pull from the nucleus on those electrons. So my atomic radius is going to shrink. Okay? So the atomic radius of lithium is going to be smaller than that of its atomic radius. Okay? So what about beryllium? Beryllium, same type of thing. So this is going to be smaller as well. And then we look at boron, carbon, nitrogen, oxygen, and fluorine. Okay? I'm not going to talk about those as the same way that I was talking about with these other ones. All right? As a matter of fact, I'm going to skip this and just go straight over here to nitrogen, oxygen, and fluorine. Because if you look at nitrogen, this is 1s2, 2s2, 2p3. Okay? And what's it going to be easier for it to do? It needs 3 electrons to get to an electronic configuration that matches that of a noble gas. Or I can lose 5 electrons to become an electronic configuration of helium. So which way is shorter? Neon or helium? And if you said neon, you are correct. If you said helium, you need to get some sleep. So let's look at it this way. So my electronic configuration here, 2p5, 2p6, right? And that's neon. So nitrogen likes to gain 3 electrons. So if I become -3 here, and this one over here is +1, -3 means I've gained 3 more electrons. My proton number hasn't changed. So what do you think is going to happen there? Greater shielding. When I have greater shielding, what's going to happen to that radius? It's going to expand. So this thing has a larger radius than its atom. Okay? Now, what about oxygen? Oxygen, can you guess the number of electrons it's going to want to get? Okay? It's going to get -2. Because its electronic configuration is 1s2, 2s2, 2p4. Okay? To get to that noble gas configuration, I need 2 more electrons. And is that going to shield at a greater capacity? Yes, it is. So this is larger, and this one is larger as well. Okay. So for the most part, when I lose electrons, from the outer shell, I'm going to see a shrinking of my atomic radius compared to that of my ionic radius for metals. And for nonmetals, I'm going to see an expansion of the radius compared to that of its original atom. Okay. For ionization energy, when we ionize any of these elements, we need to look at this and recognize it for what's happening. Ionization energy means we're knocking off an electron. Okay, so we're removing an electron for each one of these. So for ionizing, this is the valence electron shell of the second row. Okay, I didn't draw the first one. But for ionizing lithium, my first ionization energy is going to be removing that electron. So at this point, all I've got is 2s0, and I've got 1s2. So by ionizing that first electron, by removing that first electron, I've attained a noble gas configuration. The amount of energy it takes for that to happen is a paltry 520 joules. Okay? So this only takes 520 joules. If I try to ionize again, I see a jump at this point. So I go to 1s1, 2s0. So I've taken 2 electrons away from lithium at this point. And when that happens, I jump up to 7,298 joules. Why do I see such a huge jump here as far as the number of joules required to remove an electron? couple of things going on. If I look at my second ionization energy, look what I'm disrupting. I'm removing an electron from the s orbital, so I'm disrupting a noble gas configuration. I take it from that stable noble gas configuration to something that is not a stable noble gas configuration. And as a result, when that happens, I see a large jump. Okay? And this is normal. Giving away electrons to get to a noble gas electronic configuration generally isn't that bad. But notice that every second ionization is going to get us to a higher energy state. That just makes sense. It takes energy to knock these electrons off. So let's look at beryllium and see what we've got. So I go to 1s2, 2s1 here, and down here 1s2, 2s0. I'll show you what the third ionization energy is. That's 1s1, 2s0. Okay. I'll give you the first energy, and I want you to try to guess what the energy is going to be here for the next one. So we start off with 899 joules. Okay. Now what about the next one? Am I going to see a large jump here? Or am I getting to a noble gas state at this point? I'm getting to a noble gas state. Okay. So I see a little bit of energy. It's about double what it is up there. Okay. Not a huge jump. But when I try to remove that third electron there, I see a gigantic jump. And it is 14,848 joules. So that's a mammoth jump. Okay, so the first conclusion I can make about ionization energy, that first ionization energies, or the ionization energies jump significantly if I'm trying to disrupt a noble gas configuration state. Okay, so that's the first one. Okay, let's go to boron. Boron's first electronic configuration state. Okay, we go to 2s0. There's a 1s2 here. 2s0, 2s2, 2p0. All right? The amount of energy that's required for this to occur is 800. Right? Why is that the case? Why did I not require as much energy as I did over here? Right? To ionize down from 2s2 to 2s1. And it has to do with the fact that I've got a full shell. I've got a full S shell. Okay? That's relatively stable. Okay? If I've got two electrons in the S shell, not as good as noble gas configuration, but I've still paired electrons, and they tend to resist change once they're paired up. Okay? So that's why this one is less than that one. Then my next ionization energy, take a guess what's going to happen. It's going to increase, you're right, by how much? It's about triple. Right? And the reason that it grows so much is because I'm disrupting that pairing in the S. And then the next one goes up by about 1200 to 3660. And just in case you thought I was pulling your leg, the next ionization energy, the fourth one for boron, goes to 25,000. All right? So, yeah, we can immediately look at this and say, all right, anytime we disrupt the noble gas configuration, we run into issues. Now, as we keep going across the periodic table, my first ionization energy here, for carbon, it's 1086. For nitrogen, it is 1402. Okay, and for oxygen, I go to 1314. Why does that drop? Okay, it's because I've got 3 electrons. This is my first pairing of electrons. Okay, so I can knock one of those electrons off and get back to just this even spread there. That's why the energy drops a little bit when we get down to oxygen's first ionization energy. Fluorine, 1681, and neon, it's 2080. Okay, and I'm going to put sodium up here. Okay, the first ionization energy of sodium is 496. And in general, that happens. We're moving down the periodic table, ionization energy decreases. So as far as trends go, for the most part, as we move down the periodic table, first, ionization energy And when I move across the periodic table, in general, my first ionization energy is going to increase. Okay? In general, I said. Okay? Notice that there are some exceptions to this along this. But in general, when we move across the periodic table, that's what we see. All right, a couple more periodic trends I'm going to put in here, and then that'll be the end of this particular discussion.